Justin Miller, Optical Physics here. We are still moving forward, looking at some potential differences, changing potential energy. And now we want to correlate it with the amount of energy that's required to assemble a charge configuration, or somewhat equivalently, the energy stored by a charge configuration itself. So imagine, if you will, that we have nothing, but infinitely far away, there's some charges that we can grab. We can move them and start building particular configurations out of those charges. So let's say that there's charges at infinity, infinitely far away, really far away. And then I'm over here in a little coordinate system that I'm working with, say. And I can go ahead and draw a coordinate system, why not? Say that I want to build a certain configuration. Maybe I want to make a circle out of, or an approximation of a circle out of 10 charges. I want to make a triangle out of 3 charges, or some sort of rectangle, or a straight line. What do? I start taking charges from infinitely far away and putting them at the positions that I want. And, well, ultimately, there's going to be energy stored in the system in doing so. Or it's going to take energy to assemble the system. If they're all like charges. So that's a little contingency here. But let's just go ahead and assume that, hey, we want to assemble some sort of configuration here. So I'm going to take some positive charge, some Q1, I pull out of here, and I want to go and put it right here, right at the origin. Q1. So I bring it from infinity, and I put it there. Does that take any energy? Well, you may say, well, if it's a mass, you got to accelerate it, you got to move it, it takes some of your energy. But I'm not really worried about my energy. I'm more worried about, or concerned with, more concerned with the energy in actually work associated with work done by the electric field. So if there's nothing here, it doesn't really require any work against the electric field, or any electric field, to put it right here. It would just be a matter of grabbing the mass, we'll stick it right there. All right, so the first one I can place there for free. There's no energy stored in the system because it's just one singular charge. You can put it anywhere. But now I want to take another charge, some Q2, and I want to put it somewhere else. Well, assume that this is another positive charge here. I take it, and as I bring it from infinity and start moving it closer and closer to this charge, what do I get? A greater and greater repulsive force, right? As I continue to move it closer and closer, that force gets greater and greater. And ultimately, what we can think of is, well, I'm moving it through a potential difference from infinity, where the potential difference is, where the electric potential is 0, to some other location, and I move it through a potential difference. And in moving that charge Q2 through that potential difference, I've changed the potential energy of the system. And there's energy stored in the system, because I just did work against the electric field. Or the electric field did negative work, so to say. So I take this charge, Q2, and maybe I put it right here. That took energy. I had to move it through the electric field due to Q1. I had to move it through a potential difference that was due to Q1. Fantastic. We can start to compute that, right? To move Q2 to its location from infinity, it had to move through a potential difference associated with Q1. So, delta PE, the change in potential energy in taking Q2, moving Q2 equal to Q2 itself multiplied by the potential difference that I moved it through, which is the potential difference due to Q1. Delta V Q1. What is delta V Q1? Well, this is, say, 0, 0, and this is the point, you say, x1, 0. And then we have that this is going to be equal to Q2 multiplied by infinity is where we started, right? Delta V, 1 divided by infinity minus, excuse me, was our initial position. Final position is 1 over x1, so we'll say k sub e. K sub e q1 divided by x1. There's the potential at this location due to q1, and then the potential at this location due to q1. It's 1 divided by infinity. It's infinitely far away, really. You can say 1. Keep putting that. K sub e q1 divided by infinity. So this is what we end up getting. We get that delta PE Q2 would be equal to K sub E Q1 Q2 divided by X1. K sub E Q1 Q2 divided by X1. It's just the potential at Q2 now multiplied by Q2. So infinity, it's the potential at Q2 due to Q1 multiplied by Q2. Fantastic. There's the energy stored in the system. Equivalently, the amount of energy that it took to put Q2 there. All right, so what happens if we take another charge? Take a Q3 from infinity. Q3, and we want to bring Q3, say, like right here. Q3 right there, and we can say that it has some coordinates y, let's call x2, that's okay. Y, call it y30 just to call it something, and say, okay, well, what do we got going on with this? Well, to move Q3 there, we had to move it through the potentials of both Q1 and Q2 combined. Still at infinity, the potential due to Q1 and Q2 is going to be equal to 0. But the potential at this location is due to both Q1 and Q2. So to move Q3 there, delta PE Q3, so moving Q3, is going to be equal to, well, Q3 multiplied by the potential difference of both Q1 and Q2. Delta V1 plus delta V2, and this is between the positions y3, 0, and moving from infinity to that point. So got to be a little bit careful with this. These potential differences are relative to these 2 points regarding these 2 charges. So again, at infinity, they're both equal to 0. So let's look at what delta V1 is. Delta V1 is the potential difference due to Q1 at the location potential difference due to Q1 regarding infinity and the location at which we place Q3, which is this Y30 in this case. Delta V2 is the same sort of thing, but it is the potential difference due to Q2 regarding infinity and the location that we put Q3. So what do we have here? Well, the distance that Q3 is away from Q1 and Q2 is this. We've got this R13, this R23, which we could figure out pretty easily, right? We've got a Y3, we've got an X1, we can figure out R23, R13. The distance between these two would just be equal to Y3. But that's what we end up getting here. So when we go ahead and calculate this out, we've got ourselves that delta PE and moving Q3 is equal to Q3 multiplied by delta V1, which is going to be, in case of E, Q1 divided by Y3 minus case of E, Q1 over infinity. That just ends up being 0. And then we've got plus potential difference due to Q2. So it's the total quantity here. We've got case of E, Q2 divided by R23, I'll call it, plus case of E, Q2 over infinity. And again, that's 0 and that's 0. Close this up and note that R23 is going to be equal to the square root of x1 squared plus y3 squared. I unfortunately call it this x1 to begin with. Probably would have been better to call it x2, but I just need to be able to keep track of stuff. There ends up being lots to keep track of, the more that we add in. All right, so we moved Q3 there, and we've got the change in potential energy here, so we can go ahead and say that this is going to be equal to case of E, Q1, Q3 divided by Y3, or R13 if you want to call it, plus case of E, Q2, Q3 divided by, I'm just going to write R23. If we want to know the total energy stored in this system, that is going to be equal to delta PE2 plus delta PE3. The amount of energy that it took to move Q2 to its position plus the amount of energy that it took to move Q3 to its position, which is then going to be equal to case of E, Q1, Q2, or X1, case of E, Q1, Q2 over X1, plus case of E, Q1, Q3 over Y3, plus case of E, Q2, Q3 over R23. What happens if we move another charge? Take a Q4 and stick it somewhere? Well, now we're moving Q4 through the potential of Q1, Q2, and Q3. And what are we going to get? We're going to get 3 more terms. We'll have a Q4, Q1, a Q2, Q4, a Q3, Q4, all divided by they're distances away from wherever we place that charge. So the more charges you add, the more terms that you get. You start with one term, then two more, then three more, then four more, then five more, and that's really it. So again, it's all just a matter of where are you placing the charges relative to the other charges that are already there. That's what it comes down to. So kind of cool little problems. Build up isosceles triangles and all sorts of cool stuff. But that's what we wanted to kind of get at. It takes energy to build certain charge configurations. And that energy that it takes, the work done against the electric field, if you will, is energy stored in the system. I take those three charges, I put them like that, I hold them in place. What happens when I let go? It's all repulsive, right? They all fly apart from one another because there's energy stored. And we'll stick with charges that are all light charges. Gets a little bit, I don't want to say messy, but different to approach if you have a combination of plus and minus. Because minus is already attracted to plus, you gotta kind of think of it a little bit different. But for now, we'll just stick with net charges being positive, or all negative for that matter. All right, so that's that for that, and that'll do. Be well.